now, it's time for us to get to know our first speaker. He is a science research specialist too at the DOST-ASTI. His past and current engagements include the Unmanned Aerial Vehicle or UAV technology development efforts for multi-purpose applications, the Automated Electronic Surveying System or the AESS, which includes the development of an internationally accredited modular electronic system capable of processing paper-based surveys with end-to-end secure result transmission. And lastly, the development of locally made AI robots utilizing machine vision neural networks capable of enhancing post-disaster efforts. He is here with us today to discuss the current state of robots, give us an overview on what the Robot Operating System, or ROS, is, the advantages of ROS, simple robot architecture, ROS robot architecture, and ROS architecture. Please welcome Mr. Joshua A. Javier.
So good day everyone, I will be your presenter for this segment of the webinar, and it is formally entitled Industry Grade and Open Source Platform for Robotics, which is ROS or ROS. So this ROS is not your typical ROS, which I think is also a name of a mobile video game. Oh, that's a different kind of ROS. So the ROS we are discussing for today will be the Robot Operating System. You might ask, what is ROS and why is it called an operating system? Well, for our people or who are watching who are a bit technical, ROS isn't actually per se an operating system. Rather, it is much more of a middleware in that regard. So before discussing about what is ROS, let us dive in first on the current state of robots nowadays. So in this slide, you can see that 3 robots are here, which is the first one you can see here is the MIT Cheetah. So developed by MIT, which is a 4-legged robot that can climb stairs, that can run, that can walk, etc. And of course, you can see here one of the most commonly used household tools, especially in developed countries and first world countries, which is the vacuum robot. So the vacuum robot, maybe you even have one of these in your household, maybe for cleaning your dog's fur, which is shedding, or maybe your cat or your pet, etc., etc. And of course, we have here another picture of a robot, which is one of the most, at least for me, is one of the most engineering marvels that humans have accomplished, which is the giant robot in Japan, which is the RX-78. And this robot actually moves. So imagine, and maybe in 50 years from now, we will have robots of this size walking down the street. That will be awesome. So starting with the current state of robotics, let us view more on what transpired for the age of robotics maybe in the last 50 years. So robots nowadays are very different from the robots of yesterday. What I mean by yesterday is 30 years ago, since robots of today are mostly integrated within society. So you can see robots maybe serving food, like the robot here in restaurants, taking orders from you, from your table, and delivering the food to you. No need of servers or any of the sort. Or maybe you can see in this airport. This is actually an airport. Maybe you can see robots as airport assistants, since if you will be traveling in a foreign airport, you don't know where this particular gate is, the robot can easily tell you where it is and even guide you to that particular location. And of course, the other side of the coin, which is for military applications. So military applications is always on the other side of the coin, where robots can also be used. Although in a humane perspective, it's not at the very least for me, it's not the right way to utilize this technology. So anyway, diving deeper on the difference between the robots of yesterday and the robots of today, because the robots of yesterday were mostly enclosed in a separate room, in a separate space. Maybe there is this big glass in between, usually in factories. Why, if you may ask? Because robots back then were hazardous, very hazardous to humans. And by hazardous, I mean that they could cause accidents easily to us operators of the robots. Unlike today, where those possible hazards has been addressed via new modern technologies, as well as they are now going into the mainstream applications as tools as a part of the everyday lives of human society. And that is where the robots are now at this modern age. So moving on how did this transition transpire and what enabled that is mostly the speed of development by the researchers and developers. And how fast a new technology is being developed in the field of robotics would mean so much more to their value. And the role of ROS in that case for the past 10 years has, or I mean 10, 20 years ago, was to speed the development of robots via providing researchers the bare bones of a functioning robot. And ROS does this in the case that so that researchers won't have to build a robot from scratch. And what I mean by that will be explained further in the presentation. So, what was the driving point of creating ROS? Or what was the history of ROS? So, ROS now is called the Linux of robotics. So, it's basically a multi platform and can be used almost anywhere as long as in the field of robotics. So, these two guys started ROS. This is the Eric Berger and Keenan Wirebreck. So, when they were doing their PhDs or when they were at Stanford, basically, these two were thinking of a topic on what their PhD topic research will be about. So they were asking colleagues, they were asking experts, they were asking their professors, or basically anyone, any researcher in the field of robotics, just to get some ideas. And what they discovered was something very different. And in the words of Keenan, they discovered that the researchers spent almost 90% of their time rewriting code, others that had written before, and building a prototype test bed. Then the last 10% of their efforts at most were spent on innovation. What this basically means is that the developers or the researchers in the field of robotics mostly spent their time recreating the current technology instead of adding new ones on top of that. So they spent 80-90% of their time and resources into building what has already been built. If you get what I mean, is that it's not very efficient. So that was the main driving point in for those two that created or started ROS. So they wanted to create some form of platform for researchers or developers such that it would be easy to use and easy to add new technologies, new ideas on top of what has currently been built. So with that in mind, they scrounged for funding for their research. And upon stumbling upon, I forgot her name, but someone from Apple or a former employee of Apple gave them the initial capital of around 50 grand or $50,000. And what they did with that money was to build PR1. So PR1 was their first prototype or proof of concept of a robot developed using ROS. So I will show you here a clip of the video of PR1. This video is sped up. Nonetheless, it is an amazing showcase of what ROS can do. So as you can see here, this is a picture of the room of their roommate, I think, or a friend of them, and the robot is cleaning up the mess. It sorts the Lego pieces as well as arranges some cushions on the couch. Okay, so basically PR1, they used PR1 to market their research and to further their advocate of developing ROS. And the fruits of their labor came true when they met this man. So this was the turning point when they met Scott Hassan. Scott Hassan, if you don't know him, he is in the leagues of like Jeff Bezos, Bill Gates, Mark Zuckerberg, those big tech names, Linus Torvalds, those big tech names are on par with Scott Hassan. And Scott Hassan, if you don't know him, one of his biggest accomplishments will be the development of the Google search engine. And Scott Hassan gave them funding since he himself developed the Google search engine via open source, so their visions match, and he wanted to pay it forward. So he wanted to pay it forward in terms of giving these guys funding, of developing a new platform for roboticists, for researchers, for developers, in order to speed up the technology in the field of robotics. So they gave him funding, and at last, ROS started. And that is where the Linux of robotics was born, or how it was born. So now that I have spout ROS here and there, let us now compare simple robot architecture versus what is the ROS architecture look like. So here's a simple robot architecture. So maybe you wrote your main program is on a NVIDIA Jetson compute board, or maybe in an RPi. But let's say for in this example, your robot or your simple robot is written on a Jetson board. And then of course, let's say you need a camera for that robot. Maybe you will attach a Canon camera. So then you will write some driver to control that camera, and you will write some code or software that will process the received data and how it will send data from the computer, from the main computer to the outside world. So basically your camera here is the controller that has a driver, an actuator, or maybe what you will attach is some form of sensor that takes in data from the outside world back to your main processing board and do some stuff with it. So basically this is a simple robot, but what makes ROS so well industry grade and well used in terms of developing or as a developer is that ROS provides those drivers, those softwares that you need for your external device to be controlled built in. So this is the ROS robot architecture. So as you can see, ROS acts some form, as I have said, as a middleware. Let's say you've built your main application that interacts with the main computer, and then you used ROS. Basically, ROS has libraries for almost any devices, and name any brand of a camera, ROS has a driver or library for that. So instead of building your, let's say you got at present you designed a robot which uses a Canon camera. We're not sponsored, by the way, in any way. So, but then later your colleague or your team member buys another brand of camera, let's say a Nikon, and this Nikon camera has way better specs than your Canon camera, and such that you want to use that instead of your old one. But now the drivers you have designed for the Canon camera is unusable because the drivers is only for that particular camera, and you need to write again software for the new camera. That is not a trivial task. If you have experienced that, I believe that isn't easy at all. So ROS makes it very easy to integrate multiple devices of different types, of different brands. It may be a camera, a LiDAR, or whatever. It may be a motor of this type. It may be a digital recorder of this type. Maybe a encoder or something, etc. ROS, with its open source platform written by professionals in the robotics industry, and it's peer reviewed. so you can be safe that those software or libraries is usable, has a minimum amount of maintenance, and is always up to date. So that is what that is what ROS is all about. So basically, researchers can just plug and play and then experiment with new technologies and new ideas. And in this way, ROS makes the development process much, much faster than developing it all on your own. That is the main selling point of ROS. And now diving deeper to the framework of ROS, I will not really go into detail with this. I will just give you a brief overview of the framework of how ROS works. So basically, ROS has this what you call nodes, topics, parameters, actions, and services. But we are mostly going to concentrate on the nodes and topics for this webinar. So what you really just need to learn for the framework of ROS is the concept of master and slave. So maybe you're familiar with that if you're a software developer. So ROS has somehow some similarity with that concept of a master and slave. So basically, ROS has one master and it has many slaves that publishes or subscribes, or do both, publish and subscribe. So in order to visualize this more in a much more easier way, think of ROS as a communication protocol, much like how the different organs in our body communicate with each other. Let's say, example, maybe you touch something hot, so your skin sends a signal to the brain, and when you touch something hot, the brain automatically sends a signal to the muscles of your hand, so that you will remove your hand from whatever you are touching, so thus removing some burns and a trip to the hospital, and maybe even you going to death. So the way ROS works is that each of those nodes, in order to communicate, goes through the master. So the ROS master in this case, in our analogy, is the brain. So from the skin to the brain, into the brain to the hand muscles. So think of each of the organs in our body as a separate node that publishes different data. In this case, different signals, and also subscribes to different data or signals from other organs. So to analyze this in a simple robot, let's say we have here a sample robot from Boston Dynamics. So for simplicity's sake, we will just have three nodes: one arm, one leg, and one camera node. So for our arm node, it has a topic. The topic, you can think of this as the name of the node, and this particular node publishes arm movements. And these arm movements can be in the form of X, Y, and Z coordinates, can be as simple as the direction, left, right, up, down, and simple as that. And it also subscribes to the camera node. Maybe it needs visual data so that it could pick something up, or maybe it could remove the arm if it's in the way of the robot. So I don't know, maybe it depends upon the design of the robot. So at this place, we don't really bother why it needs the camera data. But in this case, those may be the reasons. So this also applies to the leg node. So the leg node, we have here a topic, which we call the leg. You can name it whatever you want. And it publishes leg movements. Again, this can be coordinates, this can be simple directions, whatever. And it also subscribes to the camera node. So maybe it needs data because it needs to navigate. Let's say it needs to go wherever direction it needs. So it needs visual data. So it makes sense that it subscribes to the camera node. And lastly, we have the camera node, which we named the topic as CAM or CAM or camera. And it publishes the video or image data. It can be a video stream, it can be a processed video stream, and it subscribes to the arm and leg node. Why? So maybe in this case, in the design of this particular robot, it needs the arm data, or the position of the arm and the position of the legs, and then it does some processing and then sends back data to those particular node in order for them to do something further. So basically, that is how ROS works, where each of them is communicating with one another, and it does something with the data that it has. One node can do something with the data it receives, it subscribes to. It's just a fancy way. Publish and subscribe, by the way, is just a fancy way of saying sending and receiving data. And as well as it applies to other nodes as well. So the arm node does something with the data from the camera node. The leg node does something to the data to the does something to the data from the camera node, and the camera node does something to the data from both the arm and leg nodes. So that is the beauty of ROS. You can subscribe to multiple nodes in this case. So basically, that is ROS, which is the open source robotics operating system that we as researchers and developers used in order to speed up the development of new technologies in the field of robotics. So before I finish this presentation and turn over it to my colleague who will present a short demonstration of what ROS can do, I say this: robots are coming whether we like it or not. Thank you very much, and this will be the first part of the webinar.